Okay, so once again, welcome you to this particular course, and I hope up to the last class, do you have any doubt? If there is any doubt, you can ask. Anyone can no. Okay, so in the last class, what we are discussing?
Inversion.
Yes, correct. So different inversion of your mechanism that we have discussed in the last class. Okay, so there basically we have discussed about the inversion of. I think my screen is visible.
Yes, sir.
Okay, so there basically have discussed about the inversion of forward mechanism. Okay, or concept forward same. So, so there we have seen that like first inversion that is application is there in the full wheel of locomotive. Second inversion we have seen regarding the beam engine, and we have seen how does it work. What kind of motion transfer happens from rotary motion to reciprocating motion, vertical reciprocating motion. It can provide. Okay, those things also we have discussed. So later on we have discussed about the pantograph mechanism in details, where we have seen that this particular mechanism can like duplicate all those different drawings, maps, etc. Or you can say you reproduce any kind of displacement in a reduced order angular space. Then we have seen about like the 14 version where we have seen about the work mechanism, or we have seen like it's a kind of approximate straight line motion mechanism that we have obtained there. Later on, we have discussed about the inversion of slider and seen all the four inversions. And I have the second inversion we have seen like the vector quick return motion mechanism, the rotary engine, etc. So this quick return motion mechanism we use in the Sept machine that you already know. Okay, so how basically like the time of cutting and time of return are related to the cutting stroke angle and return stroke angle. So here the relationship is something like that. So the ratio of time of cutting to the time of return is equal to the angle of like cutting stroke angle by return stroke angle. And as it is like 360 degree that is there throughout the circle, so we can either replace cutting stroke angle by return stroke angle by 360 degree minus cutting stroke angle, or return stroke angle also can be replaced with cutting stroke angle, but that's by doing 360 degree minus that cutting stroke angle. Okay, so these things already have. Later on we have the third inversion and fourth inversion. I just told you to go through it. So here also like another quick return motion mechanism, that is the crank and slotted lever, which is one of the common type of quick return motion mechanism that we get here. So your task will be to just compare both the type of quick return motion mechanism. Just you can consider this as a kind of assignment. Okay, so all of you try to see okay what is the basic difference between the these two type of quick return motion mechanism. Okay, both
Sir,
of
you are
them
not
have
audible,
the.
sir.
Okay, so to others, am I audible to others? What
Yes,
about
sir.
the others?
Complete.
Okay, so please, who is not listening to me, okay, who is not hearing me, just check your connection once, okay? Others are okay with that, I think. Okay, so next, the 14 version is basically in the hand pump that we see the application there. Okay, so today we are going for like the inversion of double slider cleansing. So here basically we have got three important inversions of this double slider cleansing. So first inversion is that we see is in the basic example is the elliptical tremor. So what happens here, if you look at this particular figure, just wait, okay. Okay, so if you look at this particular figure, here we are just showing it in terms of some configuration diagram. How basically like what are the different elements that we have got here and what is the look of it. So basically this electrical thermal is nothing but kind of you can consider like an instrument which you can use for drawing ellipses. Okay, so now in this particular inversion, how to get this inversion, how to get this particular mechanism out of that particular double slider pinch. So now this inversion is obtained by fixing the slotted plate. So here you can see if I have shown three different diagrams. So two are this particular videos. This is the Excel loop, okay, the middle one. So here just for the sake of understanding, okay, the left hand side how to draw and all. And in the right hand side direction, you can see another GIF, okay, where through the line diagrams, line it is represented like that. Okay, so now Here we basically have a particular plate which has got a kind of two straight groups cup on it. Okay, you can see this particular thing. Okay, the plus sign kind of symbol, these are nothing but the kind of the two groups that we have, and both the groups are orthogonal to each other, that is 90 degree to each other. Okay, so here in this particular figure you can consider this as a one of the group, and this is another group which is cut on this kind of plate. Okay, this is the whole actual system. So now, how to obtain this particular inversion, basically we have to fix this particular plate where we have got those particular groups. Okay, now if you look at this particular left hand side diagram, so we are actually denoting this slider. We have got two sliders here. Okay, so double slider. So here in this particular figure, the yellow portions are nothing but the sliders. Okay, and here in this left hand side diagram, so this portion, that is link 1 and this link 3, they are nothing but the sliders, and they are actually connected by this particular arm, as you can see in the second figure, the red arm. Okay, it is pin jointed here. Okay, and it is kind of extended kind of arm. That means it is not only joining these two slider, but is extended. Okay, as it is evident in this particular second figure. So this two blue sliders which is sliding along this particular loop, if this arm is connecting these two, along with that this arm is actually extended. Okay, so now here the link 1 and link 3, that is this link, that is the slider. Okay, and this particular slider, actually they are the sliders, and they are forming the sliding pair with link 4. Because if you consider link 1 and link 4, that group, it is basically giving you the guidance. Okay, so link 1 and link 4, that is the frame, or it is acting like the frame or the kind of guide, and it is giving it is allowing, or it is restricting the movement of the slider along this particular part. It cannot go somewhere else. Okay, while it is in motion. And what happens, they are producing sliding pair with this. Okay, 1 and 4, they are sliding pair. 2, 3 and 4 also sliding pair. And link AB, which is basically connecting this particular two sliders, here it is numbered as 2, and it is in the form of a bar, and it is forming turning pairs at this particular pin joint. Okay, you see they are actually joined with two pins at the slider. So at those pin joint, basically it is forming turning pairs. So you can see the type of movement it can have, the turning movement it can have about the point in the about that particular hinge joint or the pin joint in the second figure. Okay, and how this yellow portion or the sliders are making sliding pair with this gray portion. Okay, and this bar, okay, at this particular pin joints, okay, it is making turning pair, and this is how it during its course of action. Basically it is also evident in this particular third figure. It is going to trace, its these points are going to trace ellipse. Okay, so if you suppose place a pen or a pencil on that particular locus of the point, which where basically the locus is kind of the ellipse, then you can expect that you can draw a ellipse, so that you can draw ellipse. Or otherwise, if suppose for a particular link you wanted to have elliptical kind of motion, okay, that means this way it should move, then also once again the whatever be the link where you want that kind of movement, you are going to fit it there. Okay, so now we can just simply we can see whether actually it is giving rise to a particular ellipse or not. Okay, so the same diagram we are drawing here. Okay, this is the this plus sign kind of thing. It is nothing but the two groups, orthogonal groups. Link 1 and link 3, they are nothing but the sliders. Link 2 is the arm, okay, which is connecting it. And right now in this particular location, it is making an angle theta with the x-axis. Okay, so let's consider link 2 is making angle theta with the x-axis, and here we can consider, if you take a particular point here C, okay, which with coordinates x comma y, then this particular portion, this length is x and this height is y, right? So that means we can consider the semi minor axis for the ellipse. Okay, that BC that distance is, we are considering like small a, and we are considering, let's consider the semi major axis, that is the AC portion, okay, equal to small p. Okay, so we already have seen that basically the coordinates for this particular point C is nothing but x comma y. So what I can write, I can write x to be, this angle is theta, right? So I can write x equal to, or ultimately here also, if I draw like this, here also this angle is going to be theta only, right? If I draw a horizontal line here, okay. So this must will be x, this distance will be. So I can write x to be equal to BC cos of theta, right? I can write like this, x equal to BC, or we can write if I draw here, this angle is also going to be theta only, yes. So I can write this x, this is once again x, this is x only. So we can write x to be equal to this length, that is BC, into this cos of this angle, cos of theta. Okay, so from here we can write cos theta equal to x by BC. Similarly, or I can write x by A, that is BC already we have considered as A. Okay, x by A we can write like cos of theta. Just give it number one. Similar is the case if you consider this y. Okay, and if you consider from this like whole triangle, okay, then this distance is nothing but y, this length is nothing but y. Okay, so this angle is theta, so we can write y equal to AC sine of theta. Okay, so from there I can write y by b equal to sine theta, because already AC equal to considered as b. Okay, so give that number, and if from these two equations if you square and add them, what you are going to get, x square by a square plus y square by b square equal to 1, and that is nothing but the equation of an ellipse. Okay, that means we can say that this particular point, okay, it is on a kind of ellipse. Okay, so the locus is nothing but a kind of ellipse. Okay, so it is giving rise to this elliptical terminal, or this particular configuration is giving rise to a kind of elliptical motion. Now if you think, let's consider the whole AB. Okay, this AB, this mass. Okay, now if you consider the C point to be a mid of your circle. Okay, so midpoint of AB is going to trace a circle. How I can say that this midpoint is going to trace a circle? If that becomes the midpoint, that's what will happen. So midpoint is nothing but, I can write AC, which itself is equal to BC, and that is the radius of the circle. Let's consider R. Okay, now if A and P, so AC and BC ultimately, okay, or you can say small a and small b. Okay, if ultimately they are equal, then what will happen? We are going to, and they are equal, and they are equal to R. Okay, their length is equal, and their length is equal to R. Then after simplification, we will get x square plus y square equal to R square, right? So that means this is a equation of the circle. So elliptical terminal, okay, mid position if we consider here, so location point, okay, so midpoint is going to trace a circle. Otherwise, in normal case, it's a ellipse only. Okay. So next inversion of double slider design is known as the Scotch-Yoke mechanism. Now what happens here? Basically, this particular mechanism we use to convert rotary motion to sliding or reciprocating kind of motion, as it is evident from the GIF here. So basically, what happened? See here we have got this particular fixed portion here, and we have got this crank here. Okay, so at the end of this particular crank we have got the slider, and the slider is placed in this T-shape portion. Okay, so now as the crank 2, this is the crank portion, we are naming it, numbering with link number 2. As the crank 2 is rotating, so the horizontal portion of this particular link, okay, it is sliding or reciprocating in the fixed link A. Okay, so we have got this whole T-shape basic link here. T-shape link is one link. The shape is something like this, and it has got grooves here. Okay, This fixed portion is link 1. Similar is this particular guide. Once again is kind of fixed and this kind of link 1. This is the crank is second link. This slider is third link and the whole T portion is fourth link. So here you can see in this particular figure. So here this rotating portion, the green one, okay, that is nothing but it is acting like the, or you can say the crank 2. And due to this particular actually configuration of this particular T, so here we have got slots here. Okay, so at the end point of this particular slide crank, we have got the slider, and during the motion of this particular rotation motion of this particular crank, okay, so along with that, as they are connected, so the slider is going to slide up and down on this head portion of the T, and as it is moving from this side to this side, okay, the locus of the crank is nothing but a kind of circle. So this side it will go up to the distance r, and that side it is coming up to the distance r. Yes, in both the side it is moving like this. Okay, ultimately this is a circle it is tracing. Pardon, the drawing is very bad. Okay, and during this course of action along this particular guide, so this T portion is sliding like this. Okay, so there are the pins link 2 that is making two turning pairs. One is with link 3 here, and another one is link 1 here. Okay, two turning pairs. And this link 4, this T portion, this is the link 4. It is also making two sliding pairs. One with link, this link guide 1. Okay, and another with this slider 3. Okay, so this is that means two turning pairs and two sliding pairs that we have got. Understood? I hope you have understood. Now the third inversion of double slider comes in, and its important application we see in the one of the very interesting coupling known as the Oldham's coupling. So now what is this Oldham's coupling? Basically, see, sometimes we have to couplings are basically some connection method you can consider like this. Okay, so here this particular Oldham's coupling we use to connect two parallel shafts whose axes are actually at a small distance apart. That means both the shafts are parallel. Okay, but they are kind of axes are at a small distance apart. Okay, so if you consider two shafts, one is the suppose driving shaft and another one is the driven shaft. Now generally in the driving shaft we have got the initial motion, and our intention if we need to get the motion to the transmitted to the driven shaft, then we should be able to actually connect. If they are not connected, we are not going to get any output motion in the driven shaft, right? Because from the driving shaft only we can expect that we are going to get the motion in the driven shaft. But if they are disconnected, we are not going to get any. So now if the situation is such that, so this shaft is here, the axis of the shaft is along this line, and the axis of the driven shaft is also parallel to it, but at a certain distance apart. Let's consider this to be the offset distance. Okay. Now in this kind of cases, to actually connect this kind of situation, okay, shafts which are parallel but axes are small distance apart. So we use this coupling known as the Oldham's coupling. Okay. This is the coupling and this is the technique. So we have basically so here in this particular case the inversion is by fixing link to from here. Okay, here you can see we have got this fence portion and one intermediate piece to access both side of the uh, subs, one intermediate piece. Okay, so that basically constitutes the main part of this voltage. Now what happens, the subs to be connected to fences basically which is acting like the this fence portion, and another fence is the second. Okay, and they are basically directly passing to the end points. Okay, and there is link 1 and link 2, they are going to form turning pair with link 2, that is the support that we have here. Okay, So now what is the basic design feature that is there, which is allowing this kind of motion transfer from one parallel sub to another parallel sub, which are actually which activate a small distance apart. Our intention is we have to couple them, okay, in such a way that when one of the sub rotates, the second sub should also rotate with the same speed. That is what is our intention. Okay, and we want to achieve that particular. Now for that, actually the this plane this, okay, this particular planes one and second planes, okay, this particular planes they have got diametrical slots that in their inner circle, inner plane, which is from here. So now here you can see this rocket portion, okay. So they basically have got some from this endpoint to endpoint, that means the diametrical slots on their inner plane. Now we have got another important thing, that is the interchange mix, okay, which will be in between the both the lenses, connecting the two lenses, and somehow it is going to connect both the lenses and allow the motion transfer to happen properly. So for that to happen, for reference, so we'll be taking a kind of circular disc, that is so you can see here, okay, circular disc kind of thing, and it has got two tongues. Okay, so two projections, you can consider two projections on its outer side. One is in this side, okay, and there another projection is in that side. Now once again, that is kind of the uh, diametrical, you can say, projection. That means throughout along this space we have got one projection, okay, projected tongue, and if this is the case, in the next phase, in the opposite side, we have got another tongue. This is tongue one, this is tongue two, and the tongue two is something like this way throughout the diameter diametrically, it is done on the opposite side. Okay, so that they matches the slots which are cut on the flange. Okay, so in the inner side of the flange, we have got slots cut, and this portion will be filled. This slots will be filled by the tongue portion from the intermediate. So this is one flange. In between, we have got the intermediate piece, which is another flange. Okay, so because after the successful happens, the tongue from the link so they will closely fit to the slots on the toothpaste. And now the link 4, that is the intermediate piece, we can slide or reciprocate the slots in the okay. Now here I think your understanding will be more proper with respect to this particular. So here this is the this is you can consider as the input sub. Okay, this blue portion is the input sub, and if you look, okay, then this X-ray and this X-ray, they're parallel, but they have got this particular distance. Okay, now we need to time. So for that we are using this particular old transfer. So this is one transportation. This portion is another transportation which is rigidly connected to both the input and output sub, and this green portion is the intermediate. And now you can see here while rotating. So actually this portion, okay, it has got diametrical cutting, so diametrical slot cut here as well as here, and this green portion has got some projection. This green portion you can see, okay, and they are matching, they are closely fitting on the slots here, okay, and during its course of action they also slide, okay, and thus they allow the motion to transfer from the input shaft to the output shaft. Okay, so the midpoint of the intermediate piece, it describes a circle with distance between the axis of the shaft as the diameter of it. Okay, and now maximum sliding velocity we can get the maximum sliding velocity by peripheral velocity along the circular path. Okay, that itself is equal to that, and the sliding velocity v can get like, we know that v equal to r omega. That is the normal case we already know. Okay, so in this case, this v is nothing but the maximum sliding velocity we are talking about, and r is nothing but the distance between the two shafts, and the angular velocity of the shaft is nothing but the omega. Okay, and that is how you can get the maximum sliding velocity there on that particular turn portion. Okay, so now you have understood how Oldham's coupling works, how it is connecting two shafts which are whose axes are kind of parallel, but they are at a certain distance apart. Just let me know you have understood or not.
So when you will be sharing this slide, sir?
Yeah, some of the things are already given to your in your Google Classroom. I believe the slides are also I have already uploaded. If not, let me know.
Okay,
Just
sir.
check your Google Classroom. Are you checking the
Yes,
Google
sir.
Classroom regularly?
No, sir.
Okay, so in the Google
I'll check.
Classroom it should be available. I think
Yes,
it's
I'll check
also
now.
okay. So up to this much, I hope it's clear. So then let's try a simple problem regarding the quick retention mechanism. Very basic one. Now, what is this question? Okay, the question statement is left, right? So here we are considering a quick return motion mechanism of the oscillating link type. Okay, and this diagram is shown here. Okay, this is the case. Now, what are the given data? So it is said that the distance between the fixed centers, here we have got this to fixed position. Okay, A, and we have got another fixed location here, that is C. The distance is given as how much? AC is equal to 80 millimeter. And the length of the driving crank is given as BC equal to, that is, this is B, this fixed portion is C, B is nothing but slider, and this crank length is 20 mm. Okay, so crank means which portion? What kind of motion does it have? Crank, it rotates or it slides, or what happens to the crank?
You rotate, sir.
Yes, correct. Okay, so now this BC distance, that is the driving crank, this one. Okay, so this distance length is given as 20 mm. Okay, now here it is said that, so it's a kind of quick return motion mechanism, all of you already know during the course of a section. So the this slider is going to slide along this particular line also. Along that, this link is going to rotate. Okay, it is going to take two extreme points. Okay, and now here in this particular portion, if we whatever will be the cutting tool, if you connect the cutting tool here, so this is how along this side it is going to have the motion, and during its course of action it is going to, in the forward stroke it is going to cut, and the return stroke should be idle, but it should be accomplished at a faster in a faster way. Okay, that means slower, slow, like you can say, uh, it will be quick return. Okay, that means it is going to take less time in the return process. Okay, and the forward that which is the idle one, and the forward stroke, actually it cuts the material. Okay, it is accomplished at a somewhat shorter pace. Okay, so now in this particular situation the dimensions are given, so it is said that the return stroke is going to complete, it is completed in within 2 seconds. Now you need to find out how long the working stroke or the forward stroke is going to take. Okay, so it's a simple problem. So in that particular case, what we'll do, initially you are just drawing this particular two extreme point position we are showing. So our ease of solving this particular problem, and this is the AC is nothing but this AC. This is the AC, that is the fixed portion. Okay, so in this particular diagram, this is the AC, which is nothing but the fixed. Okay, and in B1 and B2, this is the B, right? Okay, so B1 and B2 are the two extreme location for the same point P in these two sides. Okay, and here this is just like here this link we have. So just a second, please. And this BC is the crank, and when the crank is rotating, so ultimately it is the locus will be a circle. Correct. So the two extreme points we are looking. So it's now from this particular diagram here, can you tell me which one? Let's consider this angle as angle beta. This whole angle is angle alpha, and half of it definitely is alpha by 2. Okay, if this side, if I consider alpha by 2, this side alpha by 2, that whole angle is. So which one do you think is the cutting stroke angle, and which one do you think is the return stroke? The smaller angle is cutting stroke angle or return stroke? We know that. Well, tell me. So bigger, which one is going to take in the quick return motion mechanism? The return portion is first or forward portion? From the name itself, it is there, no? Shankar is trying to say something. Shankar, you have raised your hand. No, nothing. Tell me. So now this bigger angle ultimately is nothing but the cutting stroke. As we know that, which one is going to get faster? Okay, which one is going to be accomplished first? Quick return. That means no one. You don't know. These things already have studied in your manufacturing technology. No? Now here this beta is the cutting stroke angle and the smaller angle alpha is the your what angle? Anyone who can tell me? Are you people here in this call or you have just joined and you have left the.
Sir, can you repeat the question, sir?
So in this quick return motion mechanism, I have asked that which angle, suppose alpha, out of this alpha and beta, alpha angle is the smaller one, the beta angle is the bigger one. So just from there itself, with this logic itself, I have asked you, which one do you think is the cutting stroke angle, which one is the return stroke angle? It is a quick return motion mechanism. No? So here this angle is cutting stroke angle, bigger one. And return stroke it is going to accomplish within this time. Okay. So now what I can draw from this particular diagram, we have I can write. So it's already given AC equal to 80 mm, BC this driving length is also given to be 20 mm, and we are showing the two extreme position of the crank in this particular figure. Okay, so I can write sine CA from this particular triangle, right angle triangle. This is a right angle triangle. This one also is a right angle triangle. Okay, so I can write from this particular triangle of ACE. Okay, so sine CAB1, that is this angle, sine CAB1 equal to B1C divided by AC. So BC is given B1C or BC, it is the same thing. It is the same crank that has just, oh, it is just rotating two different positions we are showing for the same crank. So it is BC or B1C or B2C, it is the same thing. BC itself is equal to B1C, that itself is equal to B2C. Okay, because this B1 and B2, these are nothing but the two extreme locations for the B point only in two different sides. Okay, so length is not going to change. So from here what I'll get, okay, this is an AC is already given in the question to be 80 mm. So just by using, so these two values I get theta to be 14.4. So now this theta is from theta, I am not interested in the theta actually, we are interested in this angle alpha. Okay, so from this triangle what I'll get, the half of this angle is alpha by 2. So alpha by 2 I can write 180 degree minus 90 minus this particular theta. It's three, all the three angles for a triangle. If I just sum those up, you already know what is the answer. Okay, so from here, just by simplification, I get alpha to be 151.04 degree. Okay, and now within that particular circle, I know that this beta I can write like 360 degree minus alpha. This is the whole alpha angle, and this is the beta angle. So beta I can write to be 360 degree minus alpha. Beta is 360 degree minus alpha, and alpha value is already there. 360 degree minus alpha is nothing but beta. Alpha value is already we have just obtained. So that's by putting this value I have obtained the beta angle, that is the cutting stroke angle to be 208.96 degree. Okay. Now we can take out the time ratio of working stroke to the return stroke, because it will be in the same ratio as that of the two angles, that is the cutting stroke angle and the return stroke angle. Okay, so bigger is the angle. Okay, that means depending on how what is the value of alpha and beta, you are going to get the time ratio of working stroke to the return stroke also. Okay, so working by return. Okay, working stroke means the cutting stroke is the working stroke, so beta by alpha. So beta by alpha, already we have got the value, comes to be 1.38. Okay. Now it is already said that the return stroke takes 2 seconds to accomplish. Okay. So if that is the case, then the time for working stroke will be how much? 1.38 times the time taken for return stroke. So 1.38 into 2 seconds is nothing but 2.76 seconds. So this is the ratio, or this is the amount, okay, multiplying factor by which actually the return stroke, working stroke is, you have to be multiply the working stroke with this particular time ratio so as to get the time taken for the working stroke. Okay, as we already know, return stroke takes 2 seconds, so cutting stroke is taking 2.76. So from these two, which stroke is faster? Return stroke completes at 2 seconds, cutting stroke takes 2.7 seconds to complete. Which is faster?
2 second, 2.76.
2.76 is faster. It is taking more time.
No,
That means it is faster.
no,
Hmm? So definitely this is return stroke is faster. No, it is completed within less amount of time. Means
yes,
shorter duration. Shorter duration means fast. Longer duration means slow. That's the simple logic. Okay. So this justifies the quick return muscle mechanism. Okay. So this kind of problems, small problems also be there. Just try this kind of solving this kind of. Okay. So you have understood how you have solved this. Just from the configuration, we are just interested in finding out the angles. We know that how the time and the different angles they are related. Okay, cutting stroke time and cutting stroke angle, how they are related. So if I know about the angle, value of the angles, we can know about the time taken also. Okay, so with this for today, we'll stop here. If you have got any confusion, any question, you can ask. No? Okay, then respond to your name first. Nilupal.
when sir?
Nilupal, why you are absent so many classes?
Sir, because I was doing my internship, sir. Yesterday I just completed. I got my certificate. So I
Okay, you
was
have been
sending
doing
you.
internship.
Yes, sir. In Indian Railway, sir.
Okay, okay, okay. Okay, okay then Shankar,
Present, sir.
Shankar, Asishman,
Present, sir.
Rehan,
Present, sir.
Arthapati,
Present, sir.
Rishikesh Basumatari,
Present, sir.
Hermiki, Hermiki, absent, Nosal,
Present, sir.
Heza, Heza, absent, Rishikesh Nath,
Yes, sir.
and Emil. Emil, absent. Okay, so this will stop here for today. Thank you everyone for
Thank you, sir.
Thank you, sir.